Well, hello one and all, and welcome back to CS50's Introduction to Databases with SQL. My name is Carter Zanke, and last we left off, we learned about relating. That is, how to have multiple tables in our database for people, places, and things, and how to have them relate to one another in the way they might do in the real world. Now, today, we'll take a step forward, and we'll talk about how to put you in the driver's seat, designing your very own database schemas to organize your data. Now, we'll pick up where we last left off, which was with this database of books. So we had this database that was full of books that had been longlisted for the International Booker Prize. To be longlisted means to be nominated for some prize, let's say. So we had the past 5 years of books in this database, and we worked on improving this database over time from week 0 to week 1. Now this week, we'll actually take a look underneath the hood and see what commands we had used to create these very databases. So let's reveal now what we had done all along. I'll go back to my terminal here. And if you remember, I could use a command to open up a database file, which was this command here, SQLite3, and then the name of the file I want to open. So let's try this. I'll go back to week 0, to my week 0 folder, like this, and I'll open up my long list database, week0/longlist.db. OK, I'll hit Enter. Now I'm in my SQLite prompt, so I could work on typing some SQL commands, SQL statements, or queries inside of this terminal prompt here. So if I want to get a feel for what's inside this database, we saw I could use a command called select. So I'll select now some rows from this table. I'll say select, let's say, the title, and also the author columns from my long list table, semicolon, and enter. Now I'll see all the titles and all the authors that were inside of this long list table. But I only want to peek here. I only want to see roughly what kind of data is inside, so I could probably improve this command here. I could instead say select the author and title columns from long list, but limit now to the first 5 rows, as we saw before. Semicolon, and I'll hit Enter on this query, and now I'll see only the top 5 rows. So I'm able now to see roughly what kind of data is inside my database. But what I can't yet see is what command was used to create this table, and what kind of data could be stored inside of it. So let's reveal now what was going on underneath the hood all this time. I'll say this new command, a SQLite command, not a SQL keyword, but a SQLite command called .schema. Now if I hit Enter, I'll see the following. The command, the statement, the query that was used to create this long list table. And notice how I have many columns inside this table. I have an ISBN column, a title column, an author column, and so on. And each column seems to have some kind of data that could be stored inside of it, like text or integers or real for floating point values or decimals, if you're familiar. So this is how we created the very first version of longlist.db. But let's also see how we created the second. So I'll type .quit to leave this version of longlist.db. And now let me open up the next version we had created, which is more relational. It had tables inside of it that could relate to one another. So let me type SQLite3, then SQLite3, and go to week 1, and then type longlist.db. I'll hit Enter. Now I'm in my next version of longlist.db. Well, what could I do? I could type select and look at some of the tables in here to see what kind of data is inside. I could perhaps say select maybe the names from the authors table here, and hit semicolon. Now I'll see all the names of authors that are inside of the authors table. I could do the same thing for books. I could maybe look at the titles of books. I could say select title from the books table, semicolon, and enter. Now I see all of the titles that are inside my books table. But what I haven't seen yet is the schema of this database. It is the way it is organized and the commands that were used to create these tables. So let me work on that now. I'll clear my terminal using Control-L. And now let me type .schema again. I'll type .schema to see what commands were used to create this database. Hit Enter, and I can see, there are quite a lot of commands here. Now, this feels overwhelming. I'd be right there with you, right? This is a lot of commands to parse through and read. So there's probably a better way to do this. And one way to try is to type .schema and then give it some table name. Let's say I want to understand the schema for just the books table, like just that for now. So I'll say .schema and then the table name, books in this case. Then I can hit Enter. Now I'll see the schema, the organization, the command that we used to create the books table in this case. And notice again, we have several columns, ID, ISBN, title, publisher ID, and so on. Each one has their own kind of data they could support or take into this column, like integers, text, and so on. So again, what we'll do today is have you all learn how to write your very own create table commands to build your very own databases that represent what you want to represent in the real world. So let me exit this prompt here, and let me propose that we'll have a bit of a design challenge today to actually try to represent a real-world entity with some database here. And if you're not already familiar, Boston is perhaps famous for being among the first cities to have a subway system in the United States. So here is a picture from the late 1800s of a subway being built in Boston's city streets. Underneath the streets here, there would be trolley cars that would go and transport people across Boston. Here's another picture of a trolley actually working underneath the streets. So people would go down underneath, they would hop on a trolley, they'd be able to go to different parts of Boston, perhaps from Harvard to the MIT, or downtown up to, let's say, Braintree, or down to Braintree, which is more south of Boston, for example. One of the famous stops is the Park Street stop, which is right down in the middle of Boston, one of the central hubs of this subway system. And now, these photos are all from, let's say, the early 1900s, late 1800s, and so on. But the subway's gotten a lot more modern since then. And actually now we have several lines that span the entire city and beyond. So here we have the red line, of which Harvard and MIT are a part. We have the green line, which brings you kind of west to east, the blue line, the orange line, and so on. So many more lines and stations have been added to this system. It's a big design challenge to represent all of these stations, all of these lines, and all of these people who might ride this subway too. So the question then becomes, how can we create a schema for this data? And again, by schema, we mean what kinds of tables should we have? What kinds of columns might those tables have? And what kind of data should we put in each of those columns, for instance? So let me propose this. Let's say we start just first with names and stations. So Charlie here, our very first rider on this system, is going to be at the Kendall and MIT station. So this is what this table represents now. But what more could we have? Well, we might also want to have maybe what Charlie is doing at that station. Maybe he's entering the station, for instance. And if you're familiar with the subway system, you often have to pay to get onto a train or get onto the station itself. So let's say Charlie pays some fare to enter into the Kendall MIT station. Well, back in the mid-1900s, the fare was only about a dime. It was 10 cents. So we'll say Charlie paid 10 cents to enter the Kendall MIT station. And now, this seems pretty good, but if I am the transit authority, the person who runs the subway system, I probably want to know, does Charlie have enough money to get on the train? And if so, I want to make sure that, okay, well, Charlie actually could get on this train. So let's say not only does Charlie pay a fare, he has some remaining balance afterwards. So Charlie here has gotten onto the Kendall MIT stop. He's paid the fare of 10 cents and has 5 cents left. Okay, so here's a bit of a table. We could probably add more information to it. Let's say Charlie then leaves at the Jamaica Plain stop. And the fare to leave is about a nickel, 5 cents. And now Charlie has no cents left over. So again, Charlie paid 10 cents to get on, had 5 cents left, paid 5 cents to get off, and now has no remaining balance here anymore. Okay, so that's Charlie's story. Let's look at Alice, though. Let's say Alice gets on at the Harvard stop. They, too, pay 10 cents to get on at the Harvard stop, and they have a remaining balance of 20 cents. Alice will go, let's say, to Park Street, get off at Park Street, pay the nickel to leave, and now they'll have a balance of 15 cents at the end. Let's go to Bob. Bob enters the Alewife station. They pay 10 cents. They have a remaining balance of 30 cents. And let's say they leave at Park Street and have a fare of 10 cents to leave because it's a further distance. Now they'll have a remaining balance of 20 cents overall. So this table is okay, I might admit. I mean, last time we learned about having what we called primary keys and foreign keys. So seems like that's missing here. Let's go ahead and add that here. I'll give each row a unique ID so I can know who entered, who exited, and so on, and give that a unique ID here. But I might even say that this table could really be improved substantially. And I want to ask you, what redundancies or inefficiencies do you see here? If we're trying to represent riders and stations, what could we improve about this design?
Hello, so probably the redundancy will be the names and the stations too. For example, Charlie will go to the train daily, then he will become most of the names in the data.
Yeah, good point. If I'm hearing what you're saying, Lauren, let me show you some examples that I highlighted here. One example could be, to your point, about these names. Like, these names seem to be telling us the name of a person, but here we have only 3 names, Charlie, Alice, and Bob. Well, my name is Carter, and what if somebody else named Carter also tried to get on and leave at some stop? Well, I wouldn't be able to know which Carter was which, or which Charlie was which Alice was which, and so on. So we probably need a way to represent people and their names a little better here, too. What other ideas do we have for how to improve the design of this table?
Yes, I think we can have a singular ID for a singular person. That way we'll be better able to track their activities.
Nice. So we could probably have an ID for each person, a bit of what we learned about last week, right? Putting people in their own table and giving them their own unique ID, a primary key. Let's show that here. I'll go to some slides, and I'll pick out one that shows us just riders. So to your point, Sukanya, we could try to have maybe a table for just riders. And maybe to simplify, this table has only 2 columns. It has a column for ID and a column for names. So here we have Charlie, Alice, and Bob all in their own table. Well, let me propose too, we could do the same thing for stations. Like, let's say we have a table of stations now, and we give each one their very own ID as well, our own primary key for this table. We have Harvard, Kendall, and Park Street, but we can differentiate between them using their IDs here. So a few improvements could be made, and as we're making these improvements, splitting one table into many, and debating what kind of data to store in each table, the process we're going through is one called normalizing. We're normalizing our data. To normalize means to reduce redundancies effectively, to take a table, take one table, for instance, split up into multiple, and have each entity be part of its very own table. Some academics in the world have named different normal forms, quote unquote. There's like first normal form, second normal form, third normal form, this progression of making your data more and more efficient. You can use those as heuristics, but at the end of the day, a few principles might apply. First, take your entities, like in this case, stations and riders, and put them each in their own table. And if you add more data, make sure that if I were to add a column, let's say, to riders, it is only a data point about riders, not about stations, not about fares, only about riders. And that process can help us make a data set that is more dynamic, more easy to reproduce, and more easy to write queries on. So that is the process here of normalizing. Okay, so if we have now riders and stations, we want to represent them in our table. Well, we could use what we learned about relating last week to ask how could we actually represent these riders and these stations. So let's say here, I again have riders and stations. I want to make sure that I have the right relationship between them. Well, if you're familiar with subways, we might say that a rider goes to one station. And this big T here is the symbol for a station here in Boston, for the T is what we call it for the subway. So a rider might go to one station. But of course, that might not be the full picture. A rider also gets off at some station later on. So a rider could be associated with not just one station, but multiple. And if you're familiar, at least with any subway system, really the Boston one too, it can often get pretty busy. And so riders might not just go to, of course, one station or two. Stations could also have multiple riders that are on a particular station here. So to recap, one rider might be associated with more than one station. They might get on at this first one and get off at this later one. But each station could presumably have more than one rider. Each station here could have rider A or rider B, the rider up here or the rider down below, and even many more than that as well. So to put it in the language of our ER diagrams, our entity relation diagrams from last week, we could look at a bit like this, where we have riders and stations. Riders visit stations, and they're associated like this. A rider must have at least one station associated with them. That's what this horizontal line means. If they aren't at a station, they aren't really a rider, right? A rider, though, could have many stations associated with them. That's what this 3 prongs down here means. They could have 1, 2, 3, 4. They could have many stations they get on and get off of. Now, a station could have anywhere between 0 riders, if it's maybe out of commission or isn't very popular, upwards to many. It could have 2, 3, 4, 5, even hundreds of riders associated with this particular station. So here is our entity relation diagram for these particular riders and these stations here. So let me ask, what questions do we have on these relationships between riders and stations, and how to design this table so far?
Sir, I want to ask that you have used the same ID for stations and riders, so that maybe give us problem in coding.
Yeah, a good observation. So you might have noticed that in the riders table and in the stations table, I gave the same kind of ID, like I had 1, 2, 3 for each of them. And let me just show you that again here. I'll come back to some slides, and I'll show you again the riders table, where we had Charlie, Alice, and Bob, ID 1, 2, 3. Same for the stations. We had stations Harvard, Kendall, Park Street, ID 1, 2, 3. And to your question, isn't that a problem? Well, I would argue in this case it's not, so long as we keep clear that these IDs are for stations and these IDs are for riders. And we'll see how to do that using our SQL keywords later on. But again, so long as we have an ID just for our riders and an ID just for our stations, we can keep these separate even if they might have the same values. But a great question here. Let's take just one more.
Regarding the entity relationship diagram, how is it possible for stations to have a possibility of 0 riders, but riders must compulsorily have at least one station?
Yeah, good question. So this might be up to you and how you formulate it, but for me, let me show the diagram again. I'll go back to over here. In my mind, to be a rider, you have to have visited a station. If you aren't visiting a station, you aren't really a rider, right? Now, presumably, there are stations that were built but aren't really being used right now, or aren't really in service yet. That could be a station that has no visitors. So you could argue, let's make sure every station has at least one rider, and every rider may or may not have to visit a station. For that, I would say, we could probably reasonably disagree there and talk about how we could represent the diagram here too. But a great observation and a good other critique of this system here. All right. So let's now turn to representing this in our database. So I'll go back to my computer, and we'll learn about this new SQL keyword, SQL statement, this one called create table. Create table allows us to, as the name suggests, create a brand new table. So let's do just that in our new database to represent riders and stations. I'll go into my terminal, and I want to make a brand new database. I'll call this one mbta.db, because MBTA stands for the Massachusetts Bay Transportation Authority, the people who run the subway, essentially. So I'll do SQLite 3 mbta.db, hit enter, and I'll type Y to say, yes, I want to create this brand new database. OK. Now, if I type .schema, I see nothing. But that's expected. I don't have any tables yet. I have nothing inside this database. It's up to me to create these tables myself. So what I'll do is clear my terminal, and let's start first with riders. I might create a table for riders. I'll say create table. And now I have to give that table some name. I might call it riders here. And then in parentheses, like this, I can specify what columns should be part of this table. So let's start first. I'll hit enter here and continue this query. Now, I'll, by convention, just indent 4 spaces, 1, 2, 3, 4, and I'll give an ID to each of these riders as we saw before. I'll say ID here is one of my columns. Now, to create a new column, I'll follow this up with a comma and hit enter. I'll again, by convention, for style, just indent 4 spaces. And what's my next column? Perhaps a name for these riders. I'll give this column the name, and I'll leave it at that. Once I'm done adding columns, I no longer need to have a comma. I could simply close out this query, this statement. I could hit enter here, say close parentheses to close the top parentheses here, semicolon, hit enter, and now nothing seems to happen. But that's actually a good sign. So let me type .schema, hit enter, and I'll see the result of that statement before. Create table, if it doesn't already exist, riders. And riders has inside of it 2 columns, ID and name. OK, let's keep going. Let's make one for stations, too. I'll clear my terminal, and I'll say create me a table called stations, and include, actually not station, if you ever want to, let's say, fix this kind of table here, let me try closing the parentheses, hit semicolon, enter. I'll get a syntax error. I can restart. I'll do Control L. Now I'll do create table stations, plural. Open parentheses, enter. I'll indent by 4 spaces, 1, 2, 3, 4. And now I'll similarly include an ID for each of these stations. I'll say ID, comma, and then what else should I have? Well, stations tend to have a name, like the Kendall MIT station, the Harvard station, the Park Street station. So I'll give each of these their very own name, comma. What else do stations have? Well, they might also have a line that they're on. Let's say it's the red line, or the blue line, or the green line, and so on. I'll have a space for them to write in their line that they're a part of. OK. And maybe I'll leave it at that to keep it simple. I'll say stations have an ID, a name, and a line. Now I'll close this out. I'll say end, parentheses, semicolon, hit enter, and nothing seems to happen. But if I type .schema, I'll now see my riders and my stations tables inside of my database. Now, one more step here. We have riders, we have stations, but we have to relate them. We have to relate them using this many-to-many relationship, as we saw last week. So let me try making a table to implement this many-to-many relationship. And if you remember, we might call this kind of table a junction table, an associative entity, a join table. It has a lot of names, but it looks a bit like this. I'll create this new table to represent, let's say, visits. A rider visits a station. So I'll call this table visits. And inside, I'll make sure it has two columns, one for a rider ID to represent a rider, and one, let's say, for a station ID to represent a station. Now, when I see a rider ID next to a station ID in this table, I'll know the rider with that certain ID visited the station with that certain ID. So I'll close this out. I'll say end parentheses here, semicolon, enter, and finally clear my terminal, type .schema, and I can see I have riders, stations, and visits between riders and stations in this associative entity, this junction table or a join table, up to you what you might want to call it in this case. Now, what questions do we have?
Why we have not used the primary key and the secondary key in this table?
Good question. So we're going to get there in just a minute, but if I look back at my terminal here, my schema, I'll see I really just have column names. And we saw before when we typed .schema on our long list.db, we had more than just column names. We had column names, we had perhaps data types, we had primary keys and foreign keys. So we'll get to that in just a minute, but suffice to say for now, we're going to keep improving this over time. Let's take one more.
Is it required to put spaces, the 4 spaces, the indents, or that's just for the visual look?
Yeah, great question. Is it required to have these 4 spaces before each column name? And in fact, no, it's not, but it makes the code more readable. So if I could put this all on one line. I shouldn't, but I could. And if I have instead this new line followed by 4 spaces, I can make this more readable for myself and for my colleagues too. Good question. Okay, so to our earlier point, there are things that are missing from this schema. Like we have column names, but as we saw before, we should ideally specify what kind of data should be able to go into each of these columns. And for that, we'll need some new ideas to talk about here. So let's focus now on this idea of data types and storage classes. Data types and storage classes are two very similar but distinct ideas, and they're distinct in a way we'll talk about in just a minute. Now, SQLite has 5 storage classes, 5 kind of types, so to speak, of values that can hold. So let's talk about the first one, null, for instance. Null, in this case, means nothing. There's nothing that actually is inside of this value. It's kind of a central value to mean nothing is here. Integer means a whole number, like 1, 2, 3, 4, 5. Real talks about decimals, like floating points, like 1.2 or 2.4, and so on. Text is used for characters. And blob, kind of a funny one, blob stands for binary large object, and it represents the data exactly as I give it to this value. If I tell it to store 101010, it'll store exactly 101010 in binary. So useful for storing, in this case, like images and video files and audio files, things that have some structure we don't want to mess around with. Now, let's focus on this idea of a storage class. These, I'll say, are storage classes and not data types in SQLite. Now, a storage class, like integer, can hold several data types. Notice how there are 7 different data types that could be stored under this integer storage class. We have a 6-byte integer, a 2-byte integer, 8 and 0, and so on. It could be any of these particular types, but each of these types is under the umbrella of this integer storage class. And SQLite itself will take care of making sure it uses the appropriate data type. Like if I give a very large number, like let's say 4 billion or 6 billion or even bigger than that, it'll probably use a longer, that is a bigger byte integer to store that kind of value. If I give it a smaller one, like 1, 2, 3, or 4, it'll probably use a 1-byte or a 2-byte integer for that. But SQLite's idea is that I, as a programmer, shouldn't have to care if I use an 8-byte or a 1-byte or a 2-byte integer. I just care that I'm using integers, whole numbers. And they give me a storage class to use any of these up to their choice here as well. Now, let's look at a few examples of values in SQLite that we could store. Well, we have perhaps the red line as some text, and because this is characters, it's quoted, we could use the text storage class to represent this particular value here. We could have maybe an image, and to the earlier point, we could say, well, this image might be best represented using a blob, a binary large object, to keep all of these pixels exactly as they are in this image. But we do get some choice, some interesting design challenges when we look at the idea of fares. So let's say, to our point earlier, fares are 10 cents back in the 1950s or so. Well, 10 cents we could store as an integer, which seems just fine. But this could get confused. I'm talking about dollars here or cents. Maybe it would be better, let's say, if I did this, a $0.10. And what might that be stored as? Well, probably text, right? I could say this $sign isn't really a number, but now I have to include it. So I'll say this will be quoted essentially as $0.10. Now there's some downsides here too. Like let's say I have I want to add these up. Well, I can't add up text. Like what does it mean to say $0.10 plus $0.20? I can't do math with text. So maybe it would be better after all if I used a real or a decimal like this, 0.10. But I mean, even here, you run into some problems. If you are familiar with how this number is represented in binary, you might know that decimal values or floating point values can't be perfectly precisely represented. And if I talk about 0.10, the computer might store 0.100000567889. It could get very wonky out to the many, many decimal digits down below here. So trade-offs and challenges overall. Let's look at these three, though. I have the first one to store as an integer. I'm trying to store fares here. Second one as text. And the third one as a floating point, or a real in this case. Let me ask for some opinions here. Which one would you use, and why? If we're trying to represent fares in this case.
Thank you. I prefer using integers because, of course, I need to get the calculation very accurately. That's my point of view. Well, sometimes I can use float, but, you know, like you said before, it can get very wonky if I get, if I really need that kind of precision. I don't really recommend using floats.
Yeah, good point. So if we go back to some slides here, you might argue for the integer because you know you can precisely represent integers. And let's say I want to add up fares over a lot of riders. This might be useful for me because I know that each number will be perfectly precisely represented. I can do lots of big kind of math with this number here. To your point, this decimal might kind of, as you should, get wonky later on towards later decimal points. I might get some unexpected results if we add up these overall. Let me ask, though, are there any proponents of this floating point value or a real value?
Okay, so I think the float is in the number of, for example, for each pair, like the uncertainty that truncation probably suggests one of the comments there.
Yeah, good point. So if we talk about using this float value, I mean, one thing we could say for it is that this decimal could be, it's more accurate to say, like, we're working with dollars now, and we could have maybe 10 cents, which is only 0.1 of a dollar. I totally hear that point as well. And the point we're making here is that they're really just trade-offs among these data storage classes to use, whether you're using integers or real values. It just depends on your use case and what you're designing for. So be sure to read up on trade-offs among these data types and determine for yourself which one should you best use. Okay, so we have now these storage classes to store values, and it turns out that columns can be made to store certain storage classes or prioritize certain classes. And the key distinction here is that columns in SQLite don't always store one particular type. Instead, they have type affinities, meaning that they'll try to convert some value you insert into a given cell or a given row to the type they have the affinity for. Now, there are, let's say, 5 type affinities in SQLite. Text, columns can be of the type affinity text, meaning they store just characters at the end of the day. There's also numeric, which stores either integer values or real values, depending on which one seems best to convert to. You have integer type affinity, which means it'll store whole numbers, real to store floating points or decimal values, and we have blob here again, our old friend, to store binary exactly as we get it. So whereas before we were talking about storage classes, those are associated with individual values, type affinities are now associated with individual columns. So let's see some example of how this might work in SQLite. Let's say I have this table of fares, and we've decided to store fares as integers. Well, if I said that this column called amount has the affinity for the text storage class, what would happen is if I insert this integer 10, it would look a bit like this later on. It would be converted to text, be quoted in this sense to represent it's now been converted to some set of characters. Let's say I insert this value 25. Well, 25 has a storage class right now of an integer. It is a whole number. But if I insert this into a column that has the text affinity, it'll be converted into, in this case, text at the end of the day. Let's do the opposite. Let's say I have my fare as a string, some text in this case. I want to insert it into this column called amount, but now amount has the integer type affinity. Well, if I insert 10, quote unquote, into the column amount, I'll get back not 10 the text, but 10 the integer. Because again, amount, this column here, has an affinity for the integer storage class. Let's try this. 25, some text again, I'll insert it into this table. Now I'll have 25 as an integer. So this is how SQLite allows us to give certain columns an affinity for certain types, that they'll try to store values of that type so long as we insert values that could be feasibly converted to that type here. So let's go back to our schema and try to improve it now to use not just column names, but also type affinities to store certain data of a certain type. Go back to my computer here, and let's improve this once more. So I'll go over to my table. And now I probably want to improve the design here. And often, if I want to improve this, I might just need to erase what I've already done. So let me introduce this new keyword, this new statement called drop table. To drop a table means to delete it, to remove it, effectively. So let me try doing this for riders, stations, and visits. I'll type drop table riders, semicolon, enter. Nothing seems to happen, but if I type dot schema, well, riders is gone. I'll try drop table stations, then semicolon, hit enter, and type, let's see, dot schema again. No more stations. I'll try drop table visits, semicolon, enter, and then dot schema. Our table, our database is really gone. There are no more tables inside of it. So let me propose that instead of working inside of the SQLite prompt, like typing out again and again and again, create table riders, create table stations, create table visits, let me be a bit more efficient about this and create myself a schema file that I could reuse throughout this lesson and also later on while I'm working on this database on my own. To do that, let me quit my SQLite prompt here, and let me type something like code schema.sql. I'm just creating this file called schema.sql. Now, a .sql file allows me to type in SQL keywords and have them be syntax highlighted so I know what's going on inside of this file. So let's just try this once more. I'll type create table riders, and inside I'll say it has the ID column of what type affinity. Well, IDs are whole numbers, so perhaps integer in this case. I could say ID has the integer type affinity. Now, let me say that writers also have a name. And how could names be best represented? Maybe text, right? Characters here. So I'll say name and text. Now, I'll include a semicolon to say this is the end of my create table statement. And before, remember how I had to kind of error out, or I had to like backspace and so on to improve the design? Here I can literally just point and click and edit this file to improve my schema. And I'll later on apply this in my database using a command that we'll see a bit later. So let's keep going here. I'll say create table stations, and inside of this stations table, I'll make sure it has an ID column of type integer, a name column that probably stores some text, and a line column that also stores some text, where name is the name of the station, like Kendall MIT, Harvard, and line is blue line or green line, what line it's part of in our subway. Let me try now visits. I'll say create table visits, and then I'll do rider ID, which has what type affinity? Probably integer. And then I'll do station ID, which has this same type affinity. We're talking about integers, whole numbers here for IDs. Semicolon to finish this statement. Now this is my schema as a whole. I have riders, stations, and visits. But now I want to apply this schema to my database. So what could I do? I could reopen it, let's say. I'll do SQLite 3 mbta.db in my terminal. And now I want to read in this schema.sql file. That is, run the commands that are inside of this file. So what could I do? I could say .read schema.sql, where .read is a command that says, take whatever file you give me, like schema.sql, and read it into this database, running any SQL keywords you come across there. I'll hit enter, and now nothing seems to have happened, but if I type .schema, I now see my schema improved. And this is helpful for me, because what I could do now is I could just edit my schema.sql file and rerun it to make sure I now have these tables being improved over time. OK, so this then is our new representation of our database. We have riders, of course, their own entity, and stations. They have an ID and a name, and stations have an ID, a name, and a line. We've also now included these type affinities, integer, text, to tell SQL what kinds of storage classes could be put inside of each of these columns. Now, before we keep improving this, let me ask what questions we have on these storage classes and type affinities.
Sir, you were using when you were creating the table was not in the line. So when we search for the authors or books, so it comes with a perfect table. So how can we make a perfect table in the SQL?
Yeah, do you mind clarifying what you mean by like the perfect table?
Sir, I mean that it was arranged in something like in boxes.
Ah, good question. So before we were able to see the results of our queries inside some boxes in our terminal. And that is actually a mode of SQLite. I think you type like .mode table to see your results in that version. Here, though, we have no data inside of our tables, so we can't really select anything from them. Like if I go to my terminal here, and I try to select some data from this riders table, let me say select star from riders, semicolon, I won't get anything back. Next week, though, we'll see how to insert and add and update and delete data inside of these tables, at which point you could write select star from riders and see some data you've inserted yourself. Great question. Let's take one more here.
Yes, I would like to know if you have a column data type Boolean.
Yeah, do we have a Boolean type affinity, let's see. So here, we don't, at least in SQLite. Some other DBMSs, database management systems, might have bool or Boolean, true or false, right? Let me show you this instead. If I go to my terminal, I can see, if I type .schema, I haven't used Boolean. There's no need for me in this case, but I have used integer. And integer for SQLite can kind of serve the same purpose. I could have the integer 0 or the integer 1 to be true, or to be false or true respectively. 0 being false and true being 1, I believe, in this case. But good question. OK, so to the earlier question, like we've improved our tables. We now have type affinities for our columns, but we don't yet have this idea we talked about last week, which was primary keys and foreign keys. This idea of trying to uniquely represent each item in our own table using primary keys and trying to reference that primary key from some other table using foreign keys. So let's try to work on that now. And for this, we'll need this new idea called a table constraint. In SQLite, you can apply what's called a constraint to your entire table. A constraint means that some values have to be a certain way. Like let's say for a primary key, primary keys must be unique. They can't repeat. And they must be, at least in our cases, going to be integers to be able to quickly like add on to them over time. Similarly, for foreign keys, well, a constraint is that if you have a foreign key, you better find that value in some other table. Otherwise, you violated this constraint of having a foreign key. So we have two kinds of table constraints, among others, but two of these are primary key and foreign key. And we can apply these to our table by applying them underneath the columns we tend to say will be inside of our table. Let's try these two here now. So let me come back to my terminal here so we can implement our very own primary key and foreign key constraints. We'll go back to my SQLite terminal and clear my screen. And let's then pull up our schema.sql file so we can keep modifying our schema. I can now see I have the riders table, stations, and visits, and I have some columns that could be primary keys or foreign keys, but I need to declare them as such. So here in the riders table, what was our primary key? Well, it was ID. Every rider should have their own unique ID that should not be duplicated across any two riders. So to ensure that constraint is applied, I could follow this up with a comma and then say primary key ID, just like this. Now ID is the primary key of this riders table. I can go down to stations and ask, what was my primary key? Well, similarly, it was ID, this ID column on line 8. So I'll type a comma, followed up with primary key ID, and now that ID column is a primary key. It has that constraint applied in stations. But now if I get down to visits, we'll have a few more options. Visits here actually doesn't have its own ID column that I created. I instead have a rider ID and a station ID column. So a few options here. One option is actually to make a joint primary key. I could have a primary key composed of two columns, both rider ID and station ID. If I applied that constraint, that would mean that if I were to ever insert a row that had the same rider ID and the same station ID as another row, I would trigger a constraint violation. Every row that has a rider ID and a station ID has to be unique in their combination of those two values. To write that kind of scenario, I could follow this up and I could say similarly, the primary key of this table is not just rider ID like this, but it's also station ID. Now this is a joint primary key constraint. But if we think about this logically, I mean, it kind of stands to reason that somebody would visit a station more than once. And I don't want to make sure that every combination of rider and station ID should be unique. I want people to be able to visit a station more than once. So maybe not the best design for this table, but I could certainly use it in other cases or other contexts. One other option would be to do what we did before and to have maybe the ID column here of type integer, and then down below, make that our primary key, a bit like this. And now visits has its own ID column. But actually, SQLite, by default, will give me its very own primary key, one called row ID. It's implicit, I can't see it, but I actually could query it. I could query for row ID, all one word, and get back a unique primary key for this table. SQLite is automatically created for me. Now, we have seen the primary key options, but what are our foreign key options? Well, it seems like rider ID and station ID are the foreign keys of this table, where rider ID references the ID column in riders, and station ID references the ID column in stations. So to codify that, to make that a reality in our schema, I could follow this up with the foreign key. The foreign key of this table is rider ID, and it references the riders table and the ID column inside of it using this syntax here. Now I could keep going. I could say I have more than one foreign key. I also have a foreign key called station ID, and that references, as we said before, the stations table and the ID column inside of it. So now here I have my completed schema. I have a primary key for the tables I've declared, an explicit column for a primary key, and now I also have foreign key constraints for those columns that should be foreign keys. So now let me ask, what questions do we have on the schema or on primary keys and foreign keys?
So yeah, I just noticed that whenever before we hadn't added the affinities and the keys, we were not applying commas after each column name. So what is the difference there?
Yeah, a good catch. Let me kind of show you what this looks like in my terminal so you can see it live. You, I think, had noticed that before we had, let's say, this primary key ID constraint in riders, we had done something like this. Let me just copy paste that. And we had removed this last column or comma from the name column. Is that right? And if that's the case, well, it's just convention, just style here. So if I want to keep adding some constraint or like a new line to my table, I should include a comma. Here, this name column was the last portion of my table I had specified. I have this column called name that has type affinity text, right? But now if I add this new constraint, we'll have to follow it up after a comma from this new column here. Notice now this constraint, primary key ID, is the last, let's say, attribute of my table I specified. I no longer need to include a comma at the end of it. So whatever is the last portion, I should not have a comma after, but everything else I should. Let's take one more question here too.
Would it be okay for the visits table to have an ID column as well?
Yeah, good question. Would it be okay for the visits table to have an ID column as well? It certainly would be. We could define our very own primary key for this table too. So let me go back and show you how that could work. I'll go to my visits table here, and I could try to add my own primary key to this table. I could say ID, make a new column here, make it of type affinity integer, like this. Let me scroll up. And now, let me add some new constraint. I could say, because I've made my very own primary key, I'll say primary key ID. Now, this table has a primary key that I've created called ID. And this will be in place of SQLites that it would have made called row ID itself, but hidden from my own view. OK. Let's keep going then. We've seen table constraints, we've seen type affinities, but we could probably do more to improve the design of this table or this database. So let's introduce one more kind of constraint, this one called a column constraint. So whereas a table constraint applies to the table as a whole, a column constraint applies to a particular column, let's say. Maybe I want a column to have certain data inside of it. Maybe I want to make sure it doesn't have null values, and so on. I could do that with column constraints. There are 4 in SQLite: check, default, not null, and unique. And each one does something different. Check allows me to make my very own check, like check to be sure that this amount is greater than 0. Or I could use default. Default means if I don't supply a value when I add a new row, it'll just use a default value instead. Not null means I can't insert null or empty values into this column. And in fact, it's required. Unique means I want to make sure that every row in this column is a unique value. It doesn't appear twice in my data set. So let's try applying a few of these to our schema here. Go back to my terminal. And now let me check out this. Well, I could try applying the not null constraint when I know I want a column to be required effectively. Now, where could I best apply that? Maybe I could apply that to the name column in stations. Like, stations must have a name. So I'll say the name column cannot be null. It cannot be empty in here. Line also should probably be not null. A station must be part of some line. I can't have an empty value for line. So I'll say, too, this should be not null. Now, I could apply this up at name. I could say riders must have a name, too. Let me try that. I'll say text not null. Or I could leave it optional. I could say maybe text just on its own and let riders choose to supply a name or not. Now, the question here is, should I apply not null to my primary key columns, like ID not null or ID not null here? You might think that you should for thoroughness sake. Well, it turns out that when you apply the primary key table constraint down below here, this already ensures that there are several constraints applied to this particular column called ID, among them being that ID cannot be null. So no need to duplicate this and say that this ID cannot be null when I already have it specified down below that ID is a primary key. Let me check others here. You might also think, could I do it for rider ID and station ID? Should I include not null here? Rider ID, not null, station ID, not null. Well, that would be a good thought, but again, we're taken care of by our table constraint using our foreign key here. Again, this constraint will say, if rider ID doesn't already exist in the ID column of riders, I can't insert that value. And we could probably presume that if rider's ID is a primary key, well, null will not be part of this column, and therefore I already can't insert null for rider ID or station ID. This would be, in this case, redundant. So not null is good when you have columns that are neither primary keys nor foreign keys, and you want to make sure that they always have a value, that they're never null, effectively. Okay, so that is not null. And we could keep going here. We also had one called unique that makes sure every value, every row in this column is unique. Where could we apply this? I could try to apply it, let's say, to the name of a station. Like, stations should have unique names. So I'll say not null and unique. Now this column has two constraints. The first, not null. It should always have a value. The second, unique. The value shouldn't repeat throughout this column. Line, I might leave without this constraint. I could imagine two stations being on the same line, like both on blue. I'll allow that in this case. Now again, we could try to apply unique to our primary keys or our foreign keys, as I just did here, but it's already taken care of for us using this primary key constraint. A primary key, again, is always going to be unique and never null. So we'll take advantage of that already using our primary key and foreign key constraints here. Okay, so we've seen unique and not null, and I might argue we're at the point where this schema seems to be fairly optimized, at least using our column constraints, our table constraints, our type affinities, and so on. So let's ask then, what questions do we have on not null and unique, if any?
So basically, to recap, if I understood correctly, it's not precisely about not null and unique, but about the concept of the key. Labeling a key immediately gives the attribute of not null, unique, and to be referenced, right?
That is true. So when you use a primary key or a foreign key constraint, there are other constraints that go along with that constraint. A primary key, for instance, must not be null. It must be unique, and so on. So it would be redundant to apply that again, to say that this primary key should be unique or not null. Good clarification there. Okay. So I think we're at the point where this schema is pretty well set for us, and we're going to need to think about, though, how we use this in the real world. Like, if this is our schema here, we have riders and stations. Well, what could we do? I mean, riders tend to, they could register for the subway. And riders, well, they do visit stations. But I think if we applied this to the real world, we'd see that this isn't quite how it's actually done. Like, riders don't really register that often. If a rider who's new to the city comes in, they want to ride the subway, they should be able to ride too. So it turns out, at least here in Boston, the MBTA doesn't really track riders per se, but they do track what we call Charlie cards. If you want to ride the subway, you get a Charlie card. A Charlie card allows you access to the subway, keeps track of your fare, your balance, and so on, and allows you to swipe in to certain stations. So when we come back from a break here, we'll see how we can actually implement these Charlie cards instead of riders to make our system more efficient and more in line with what happens in the real world. We'll see you all in just a few. And we're back. So we saw last time this challenge of designing a system for the Massachusetts Bay Transportation Authority to represent riders and stations, people who get on a subway to go around Boston. But as we also saw, we learned that the MBTA doesn't keep track of riders themselves. They keep track of Charlie cards, this card that a rider might carry in their pocket. And they can scan this card at a station to enter or even to exit in some cases, to make sure that their fare is counted as they enter that station. So let's think now how to improve our schema to represent not just riders like me, but Charlie cards themselves people might carry around when they enter the subway station. Well, we saw before, we had riders and cards, but our goal now is to remove riders from the picture, focus only on cards. Well, cards, as we've seen, might make a swipe at a station. If I enter Harvard Station, I might swipe my Charlie card to enter that station. And we could see that a card would have maybe many swipes involved. Like if I swipe at Harvard, I might also swipe at MIT or swipe at Park Street, and so on. We could see that a swipe can only happen at a single station at a time, though. Like if I swipe at Park Street, I'm only swiping at Park Street here. And similarly, a swipe might only involve one single card. So if we think about these entities and how they relate, we could also think about what kinds of columns we should have inside of each entity. In this case, I would argue we should have something a bit like this. We could say that a card has an ID for its primary key, in this case. Similarly, this card makes a swipe, and this swipe has itself an ID, as well as a type, some time that swipe happened, and an amount or a transaction that is involved. So for example, let's say I swipe in at the Harvard Square station. That type of swipe might be to enter the station at some certain time. Now, associated with that swipe is also some amount in dollars that happened to be subtracted from my card. Like let's say the fare nowadays is $2.40. Well, that amount is subtracted from my card from this swipe. Now, of course, I do all of this at a station, which has our same columns from before, ID, name, and line. So a similar idea now, but we're replacing riders with cards and adding more information to these visits. They're instead swipes that could be maybe entering the station, exiting the station, or just adding funds to my balance, for instance. So let's see how we could improve our schema now using some new SQL keywords to alter our tables and add some new ones too. I'll go back to my computer and let's see how we could try to alter the tables that we've already created. Like we already have a riders table, a visits table, and a stations table, but we could learn some new statements, some new queries to actually update and alter these tables as well. The first one, as we saw a little bit before, is this one called drop table. Arguably the most dramatic thing you can do to a table is just drop it, delete it like this. So let's try just deleting the riders table from our database. I'll go back to my database here. I'll type SQLite3 mbta.db to pull up this database again. And now if I type .schema, I'll see I have a riders, stations, and visits table. But no longer do I want to have the riders table. I want to remove that. So I'll say drop table riders, semicolon. Now I'll hit enter. no more riders table. If I type .schema, that's gone from my database. Well, what could I do now? I've dropped the table, but I'd still need to maybe update visits to instead be swipes. I could probably leave stations as is, but I want to update a table or alter its schema. I can use some new commands as well. I'll use this one called alter table. Alter table looks a bit like this. I can use the alter table statement here and give it some table name. Like let's say alter table visits. And then inside this visits table, I get to ask, what do I want to do? Do I want to, let's say, rename the table? I could do that. I could also decide to add a column, rename a column, or drop a column altogether. Let's try first looking at rename to. I want to rename this visits table to a swipes table, representing not just a visit to the station, but a swipe of a card. So let's try this one here. I'll go back to my computer, and I'll go back to SQLite, and I'll say, I no longer want visits to be called visits. I ideally want visits to actually be called swipes. So let me try this. I'll say alter table, as we saw before, visits, rename to swipes, like this, semicolon. Now I'll hit enter. And now if I type .schema again, I see, oops, kind of strange, I'll type .schema again, I'll see swipes, no longer called visits, but now called swipes. Well, we saw I'd ideally like to add a type of the swipe. Maybe I'm entering the station, maybe I'm exiting, maybe I'm just adding funds or depositing some funds. So let me try adding, let's say, a new column to swipes. I'll say alter table, add column, alter table, swipes. I'm going to name that table swipes, like this. And then let's add a column called type. And this will have the type affinity text. I'll hit semicolon, enter, and now if I type .schema, I'll see, well, I have a column called TTPE. So clearly I made a typo here. I had rider ID, station ID, this new column down below called TTPE. I kind of want to fix this, right? I don't want TTPE, I want type. So probably a good chance to use my rename column. I'll come back here and I'll try that. I'll instead do alter table, swipes, and I will rename a column now. I'll say rename the column TTPE to type, spelled correctly now. Hit semicolon, clear my terminal, type .schema, and now I see over here that type has been added to my table of swipes. I see rider ID, station ID, and now a new column called type. So through alter table, can we go ahead and add new columns, rename them even, or if I wanted to, just drop the column altogether. Let's say I add this column type and I change my mind. I don't want it here anymore. I go back to my computer and I could try dropping a particular column. Let me try, in this case, alter table, swipes, and now let me drop column type, semicolon. Hit enter. And now if I type .schema, I'm back to where I began. So these are the commands we can use to alter our tables, to improve them if we make a mistake during our first create table command, or if we want to add more functionality later down the line. So ideally, I could keep using, alter table, add table, create table, drop table, and so on. But what I want to do here is just probably start from scratch. Like I have, stations and swipes and so on. Why don't I just go back to my schema file and use that instead? So what I'll do is I'll drop table for stations, and semicolon. I will drop table for swipes now, semicolon. I'll type .schema, and now I'll see nothing in here. I'll quit, and I'll type code schema.sql. Let me just start from scratch using this schema.sql. So we no longer want to have riders. We only want to have cards. So I could just rename this table here. I'll call it cards, create table cards. Now cards don't have a name, they only have some unique ID in this case. Now, I'll leave stations just as it is. This seems perfectly fine to me. Stations have an ID, a name, and a line with these constraints applied to the name and line columns. But now the visits table. Well, the visits table is no longer a visit to the station per se, it's more a swipe of the card at that station. So let's now say visits becomes swipes. And among these new columns to add are the following. I want to have not just an ID for each swipe, not just an ID for rider ID and station ID and so on, but also I want to have a type of swipe. Am I entering the station, exiting, or depositing some funds? So I'll say the type of this is going to be a new column, and the data type this holds will be text, enter, exit, or deposit for some funds. Now let me try another column too. I'll include a date time. A date time is like a timestamp. What time did this swipe actually happen? And I'll make this type numeric. Numeric can store all kinds of dates and times for me in this table. Now, let me add one final column. This one will be an amount. I'll also use numeric for this kind of column here. And I'll say that this column, called amount, can store, in this case, integers or real numbers like floats and so on. I'll probably decide on that when I actually add some data to this table. Okay, so here we've updated our schema to represent that diagram we saw before. I have cards, I have stations, and I have swipes that have some type associated with them, enter, exit, deposit, some date time, and some amount that was charged to me while I made this swipe. Either I added some funds, in which case amount is positive, or I subtracted some funds by entering or exiting, in this case from the station. All right, so I have these tables now, and now I want to probably apply some of those same column constraints we saw before. Like here, it's fine, but I also want to make sure I'm not adding some data that I don't want to add to this table. So I could go back to my old friends, these column constraints. And we saw before, we had default and not null, unique, and check. We've used not null and unique, but we haven't used check or default. So let's start using more than just not null and unique, and also focus on check and default, what they can do for us here. I'll go back to my schema. And let me just make sure that I'm making all the columns that I want to be required actually required. I'll go into my swipes table, and I'll say that type, this should be required. I should know whether I entered, exited, or deposited some funds. So I'll say text, not null. Similarly, for the timestamp, the time this swipe happened, I want that to be not null as well. I must know what time I swiped the card. And also, it makes sense for there to always be some amount associated with this swipe. Either I added some funds to my balance, or I removed some funds overall. So I'll make this not null as well. Well, let's see what we could do here with default. Default gives me some default value, some initial value to add to this column if I don't specify what kind of value to add. This could be good for date time. Date time here is, again, the time stamp, the time I swiped this card to enter, let's say, Harvard Station. Well, if I want this to always have the current time, I could use default. I could say the default value for this column is this special value here, current time stamp in all caps. Current time stamp will show me the year, the month, the day, the hour, the minute, the second, all in one value, and insert that into my table. So as soon as I add a new row, if I don't supply a time for this date time column, I'll instead get back the current time exactly as it is represented in SQLite. Now, what could I do further than this? I could also try to add my very own check. Maybe I want to make sure that the amounts here are never equal to 0. Like, nobody should ever be able to make a $0 transaction or a $0 swipe. They're always being charged some money, or they're always depositing some money in this case. So I could say amount here has my very own check on this column. And inside check, I could actually write my very own expression to check for. I could say, for example, amount is not equal to 0. Using those same operators we saw back in week 0, this will ensure that any value inside amount will not be equal to 0. Let's try it also for type. I mean, type can only have a few values. We saw enter, exit, deposit some funds. I could make sure that only those values are included inside my type column. I could say check that type is in some list of values. Going back to week 1 here, we talked about in. I could say maybe the type is in enter, exit, or is in deposit. So now, when I have this table called swipes, I'm representing what I'm actually doing when I go to Harvard Station. I have here a visit from myself, my very own ID here, which I'll update in just a second. I have a station ID, where I'm actually going to visit. I have a type that I'm going to use to enter, exit, or deposit some funds at this station. I'm doing it at a certain time, and I have an amount associated with this transaction. Now there's one thing to fix here, which is that we're still talking about riders inside our swipes table. So let's fix that here too. I'll go back to my computer, and let's try fixing this. I have a rider ID inside of my swipes table, but no longer do I have riders, I have cards. So let me say that this is now a card ID, and down below in my foreign key, I'll say that this card ID column references the ID column in cards. And I think this should represent everything I want to represent about swipes at the station. So let me ask now what questions we have about this new schema and the constraints we've applied.
I wonder how could you delete or drop a table riders when you use ID as a foreign key? I tried to do that, but I got an error.
Yeah, so you're getting into some more advanced stuff here. And suffice to say, for now, my foreign key constraints aren't actually being checked right now, but yours might be. If you try to drop a table that has some data that's referenced by a foreign key, SQLite will warn you, perhaps just tell you, you can't do that because this ID is referenced from this table over there. So in that case, best to delete the value that has that foreign key and then proceed with dropping that table altogether. Good question there. Yeah. Let's take one more.
How much the syntax same the other SQL languages, same as SQL languages? How much the syntax same?
Yeah, good question. So here we're using the SQLite database management system. It is similar to, but distinct in some ways from others like MySQL or PostgreSQL. I would say that most of what you're doing here could also be ported to MySQL and PostgreSQL, with a few exceptions that you might need to treat on a case-by-case basis. In fact, the developers of SQLite built things so that it would be easy to port their database schemas to another schema like MySQL or PostgreSQL as well. But good question there. All right, let's take one more question here.
Imagine if we put in the ID, we don't put any data type, it's going to give us, in the schema, it's going to give us a text or...
Yeah, great question. So you're asking if I didn't tell SQLite what kind of type affinity a column had, what type affinity would it actually have? A great question. In this case, by default, SQLite gives the numeric type affinity, where numeric can store integers or real values. But if you give it like a string of text, like let's say redline, it will store that for you too, non-intuitively, but it will. But the default type affinity is numeric in this case if you don't otherwise specify. Good question. Okay, let's come back then, and let's focus on wrapping up on a final few pieces here. So we've seen some table constraints, which we applied primary keys and foreign keys. We saw column constraints, where we could make sure that certain values were given to us through not null. We could also make sure that let's say the value is in some list of values using check, or making sure that it's not some value, also using check as well. Default allows us to specify a given value for every new insertion of rows here. And this is actually pretty important to have, not just schemas that have column names and let's say type affinities as well, but also constraints to make sure the data we insert works well for us. And there's actually a story behind this person who's on the Charlie card. This person who's on the subway, his name is Charlie, and he's perhaps the most famous subway rider in all of Boston. Back in the mid-1900s, the band called the Kingston Trio wrote a song about this man named Charlie. Charlie supposedly got on at the Kendall Square station where MIT is, and he made for Jamaica Plain. But once he got to Jamaica Plain, the conductor asked him for one more nickel, and well, he didn't have that nickel. So he got stuck on the train for years and years and years and couldn't get off of the subway. So keep in mind, Charlie, when you're writing your own database constraints, making sure that if you get on the train, you're able to get off of it at some point, right? Don't end up like Charlie in this case. So with this in mind, you're able to design your very own database schemas that keep not just certain columns involved, but also type affinities for those columns, types that those data types those columns can store. You're also able to apply constraints to those columns to make sure that the data you're inserting is the data you actually want to have in that column. Next time, we'll focus on actually adding data to our columns, to actually write data to a database file, to insert, update, and delete that data altogether. So with that in mind, we'll see you next time.